Hi everybody, and welcome back to my organic chem videos. This is Maria Thomas, and today we'll talk about organometallic reactions. We're going to focus on the type that involves something like lithium aluminum hydride or sodium borohydride, not the Grignard reaction. And this is more of a review and a recap, and I hope it's useful for you. So let's start by taking a look at the structure of lithium aluminum hydride or sodium borohydride. So if you look closely, you'll notice that both of them look pretty much the same. The only difference is that you've got an aluminum here and a boron here, and you've got a lithium ion versus a sodium ion here. So like you might guess, they're both going to behave pretty much the same. So let's just focus on one of them. And I want you to look at the bond that one of these hydrogens has to the central atom, in this case an aluminum. So if you compare the electronegativity of the aluminum versus the hydrogen, it's actually the hydrogen that has a higher electronegativity than the aluminum. The same applies to boron versus the hydrogen. So in that case, where would you expect the electrons in the bond to be? You would expect them to be much closer to the atom with the higher electronegativity. So now, if you use the electrons in this bond to go and attack something, you would expect them to go along with the hydrogen. And this structure actually is called a hydride. That's an H minus, and that's very, very reactive. The hydride is also a strong base, which means you're in basic conditions at this point, and you're free to form as many negative charges as you want. So let's take a look at a reaction that actually involves this. Here we've got a pi electrophile with a leaving group and your reagents. Let's draw them out a little big so we can all see. So the area of low electron density, like we've often seen, is the carbonyl carbon, and the area of high electron density is this bond, which goes along with the H as the hydride to attack that. So let's go ahead and do just that. Push these electrons up, and you get something like an O minus. And these electrons in the bond that we use to attack actually go along with the H like we talked about, and you get this new bond forming here. But what happens to the LiAlH4? Well, as you can see here, the aluminum is sort of left without an octet, so it actually wouldn't mind hanging out with someone who has a lot of electron density. So we sort of show the electrons that formed that lone pair in the oxygen that gave it the negative charge as sort of making a bond between the oxygen and the aluminum. Let's go ahead and remove that negative charge from the oxygen because we just used that, and put that negative charge now on the aluminum. But keep in mind that on the actual periodic table, aluminum, boron, etc. occupy the third column, which means that they have 3 electrons around them and would actually still have been okay with just having 3 bonds around them. Also, oxygen has a much higher electronegativity than the aluminum, so these electrons are much closer to the oxygen. Which means that if this bond goes and attacks something, those electrons would go along with the oxygen and not the aluminum. What we've actually got here is a tetrahedral intermediate, and this does have a leaving group, which means we need to kick that off. So what electrons do we use? The ones from this bond would come down, kick off the leaving group, and those electrons would go along with the oxygen for the reasons we just talked about now. And that would give us these 3 structures, and if you notice, we've got another pi electrophile, the leaving group that's been kicked off, and the aluminum, which is alright, just having 3 bonds with 3 hydrogens. But considering that we've just formed another pi electrophile, we need to do this reaction one more time. So now, in the exact same way, another lithium aluminum hydride comes and does the exact same thing to give you something like this. Now you can see that you're forming a second bond with the second hydride. And the ALH3 again sort of goes and forms a second bond, something like a bond with the oxygen, but the electrons are still much closer to the oxygen than the aluminum. And there's that negative charge on the aluminum. And now you'll notice that there are no more leaving groups available here, which means you cannot collapse this tetrahedral intermediate and make another pi electrophile, which means that the lithium aluminum hydride is done reacting. So that means we can move on to the second step of the reaction, which involves H3O+, or acid. So acids donate protons, but who do you think is going to come and grab one of these protons? Well, if you were thinking the electrons from this bond, you're right. And let's break that bond, and you get to form this alcohol, which is your final product. And if you'll notice, the ALH3 gets left behind again, but that's okay because Al does not mind having just 3 bonds. So let's do a quick recap of what we talked about today. When the electrons in the bond here of the lithium aluminum hydride goes to react with something, the electrons in that bond would go along with the hydrogen, since the hydrogen has higher electron negativity than the aluminum. So what you're using actually is this hydride ion that's pretty basic. So when you use it to react with something with a low electronegativity like a pi electrophile, you end up forming something like this, which is a pretty normal tetrahedral intermediate, with the exception that the ALH3 sort of likes to hang out with the oxygen and form this sort of a bond. And now if your tetrahedral intermediate has a leaving group, you can go ahead and collapse that. Remember, you're in basic conditions. You can leave it without having to protonate it, which means you end up forming another pi electrophile, and that means you have to do the same reaction again. Also note that the ALH3 sort of got left behind. And so you do the same reaction a second time to get another similar looking tetrahedral intermediate. The only difference is that in this case you actually do not have a leaving group like you did previously, which means that you cannot collapse it, which means that the lithium aluminum hydride is done reacting. So now you can move on to the second step of the reaction that actually has some acid present, H3O+. So please note that now you're switching away from the basic conditions into acidic conditions. So you can use this bond to grab a proton and form your final product. And actually, if you used NaBH4 instead of lithium aluminum hydride to perform the same reaction, you would use a very similar mechanism. I hope this video helped you get a better grasp of organometallic reactions. Thank you for watching.